Hi everyone, this is the first video of PHY104. We are going to talk about electric charge, electric force, and electric field. Then, what do you see here? Okay, so what you can see, there are the children with their hairs up, and it means a cat in which some of the small objects, like light objects, got attracted to him. So this is what is happening, okay, when you have electric charge. This is what is called the electrostatic effects, okay? So the hairs of the children, okay, they kind of like pointing up because some electric charge within the hairs, they have the same type, they have the same types and they repel each other's. But for the case of the cat fur and the small objects, maybe the foam, polystyrene foam, or anything, they tends to have different types of electric charge. So different types of electric charge will attract. Okay, so we are going to see the detail in the lecture. So the outline for today's lecture is about electric charge, Coulomb's law, electric field, and electric field from the big object. Okay, so today we are going to talk about the theory. Okay, and we are going to go through the detail in the examples for all the calculations in the live class. Okay, firstly, I would like to talk about the atom. So the atom is known to be the smallest stable unit of matters. The atoms will compose of the neutron, proton, and electron. So the electrons are orbiting or making a circular motion about the neutrons. And so we talk about particles comprising atoms. Okay, so as I mentioned before, there are the uncharged or neutrally charged particle at the nucleus part of the atoms. We call it neutron. And there are also the charged particles. For the positively charged particles, we have protons. And for the negatively charged particles, we have electrons that is orbiting around the nucleus. And for the fundamental charge, the fundamental charge is the smallest amount of charge existed, which is equal to the charge of an electron, or 1.62 times 10 to the minus 19 Coulomb. Okay, so that is representing one electron, just one electron. Okay, and we say that the amount of charge for an electron is minus E, and the amount of charge for a proton, which is the smallest one, is plus E, while a neutron has no charge. And the electric charge in matters are found to be the integral multiple of E, such as 5E minus 19. So minus 19, you might have like 19 electrons. So 5E, you might have like 5 protons, or even minus 2 millions E. Okay, but we are not going to have something like 1.5. No, not 1.5 E, not 2.3 E, but just only 1 E, 2 E, 3 E. Okay, and we know that the opposite charge will attract. For example, if you have a positive and negatively charged sitting next to each other, and they will attract, and the same type of charge will repel. Okay, so this is what you might see from the pictures before. Okay, so if we imagine that the hairs of the children all have positive charge, the positive charge will repel each other, and for the cat, if we say that the cat has negative charge and the polystyrene foam has positive charge, they will attract. And then for electric charge in conductor, so in conductor, there are the mediums where charge can move relatively freely, such as metals. And within the metals, there are free electrons. So free electrons, as you can see from the animation, they kind of lose the bound nuclei. So the nuclei, they are in yellow, and electrons, they are in green. And then electrons can be moved between atoms. They can jump from here to here, from here to there, everywhere. And for the positively charged nuclei, can only vibrate with small amplitude without translation. So the yellow positive charge here cannot move far away. It's just vibrating around the center. So conductors are normally neutral, meaning that the amount of positive charge in yellow and is equals to the amount of negative charge. Okay, so normally, so I say normally, that is not always. Okay, sometimes we can also put some charge into conductor, or we can remove some charge out of the conductors. Okay, so from this animation, if we bring a negative charge object close to a conductor like this, so you can see that the free electrons or the negative charge are repelled. So this is negative charge in red. They are repelled to be far away from the rod to the right hand side. And but the nuclei in blue, which having a positive charge, they're not moving. So you can see that on the left hand side of the surface here. So if you try to count the number of the total charge here, you can see that the total charge on the left hand side will become positive. But then you can see that the charge on the right hand side, the total charge will be negative, because you can see that, okay, there are positive charges, but there are a larger number of negative charges. So that we can say that the left side of the surface, they lose electron to the right hand side, and the charge will become positive. But the right hand side of the surface, they receive electrons and they become negative. Okay, and then charge transfer by friction. Okay, so we can try to rub two objects, such as if you rub the rag, the clothes, with the PVC. Okay, so you can see that some of the negative charge will flow from the rag to the PVC, so that the rag has lose some electrons and become positive, and then the PVC will receive some electrons and become negative. Okay, and we say that the object that losing electron will be positive charge, and the object with high electron affinity, such as clothes, will receive electrons and will be negatively charged. Okay, so we have the chart here we have the diagram here to say that which one will have the high electron affinity. So the one on the downside, such as ebonite, polyester, vinyl, rubber, amber, wood. These are the objects with high electron affinity, so they have the high tendency to gain electrons. Okay, and then the charge transfer by contact. Okay, so you can also give the charge between objects. Okay, so if I have a spherical conductor here, and I bring a rod with negative charge on it, so when I touch the rod on the metal sphere, you can see that the charge, negative charge, will be transferred from the rod to the metal sphere, and after that, the charge will repel each other, and all the charges in conductor will be at the surface. Okay, this can happen because in the conductor surface, within the conductor, the charge can move freely, as we mentioned before about conductor. So when the charge can move freely, they kind of repel each other and they ends up at the surface. And another way of charge transfer is the charge transfer by induction. The charge transfer by induction happens when bringing the charged object near the conductor. So if I bring the negatively charged rod near the metal conductor, okay. So at the first step, we can see. What we do here, okay, is bringing it near, but not touching, no touching, but just bringing it near. And we can see that if the charge can move freely in a conductor, okay, a negative charge electron will choose to move backward because negative charge in the conductor will be repelled by the negative charge in the rod, okay? And then when the negative charge, okay, just like in this picture, when the negative charge is repelled, the left-hand side will be positive charge, and that because it loses electrons. And the right-hand side will be negatively charged because it receives electrons. So it's the same picture. But then, if you try to connect the right-hand side with the ground, okay, the ground will allow the charge to flow out to somewhere else. Okay, so when we separate the positive charge and negative charge in A, and then we drain out the negative charge to somewhere else, what left in this picture is the positive charge. So that for the picture C, this sphere will become positively charged. Okay, so this is the charge transfer by induction. Electroscope. This is another applications of using the induction phenomena of charge. So an electroscope is a classic instrument for the charge detection. Okay, so what we have for an electroscope is a disc. So this one is made from brass, or it can also made from any conductor. And then we connect the brass to the gold leads, or it could be any like metal foils, anything. Okay, so what happens is for the electroscope is we try to bring some charged object near the metal plate. So the induction that happens, okay, the positive charge will be repelled from the positive charge, and the negative charge, actually the one that is moving were negative charge of electrons. So electrons will be moved from up to the plate, okay, so that it will be attracted by the positive charge. And then what left in the gold foil is, and for the gold foil, they lose electrons and they become positively charged. And then when both of the foils having positive charge, they repel each other, and then they tends to be separated. Okay, so that's with the gold foils or the metal foils separated. Okay, we can tell that in the rod or in the object that we bring it near the disk, there are charges on it. Okay, but if there's no charge on it, this separation of the gold foil will not happen. Okay, so now we comes to a little bit of calculation using Coulomb's law. So as we mentioned before about the attraction and the repulsion of the charge, with different sign you attract and same sign will repel. Okay, we can quantitatively, okay, or we can put that into equations, okay, by Coulomb's. So Coulomb's law, for Coulomb's law, we consider two objects, or we can say that it is two charge, okay, two object with charge. We say that it is a Q1 and Q2, and then when we bring Q1 and Q2 to be within the distance R, okay, there will be force acting on 1 by 2. And there will be force acting on 2 by 1. And Coulomb's law says that the force between two charges will be proportional to Q1 and Q2. So that means if Q1 is large, the force will be large. And with Q2 larger, the force will also be larger. But is inverse proportional to the square of the separation distance. Okay, that means if I separate two charges to be further, the force will be weaker. The force will be weaker. But if I bring two charges closer, okay, the force will be higher. Okay, so if there are the repulsive force, if I bring two charges very close, they will repel each other very hard. Okay, but if I start with two charges far away from each other, they are not going to push each other too hard. Okay, so with the proportionality of Q1, Q2, and inverse R square, we have that the force will be proportional to Q1, Q2 over R square. And then we put in a constant, K, which is called the Coulomb constant. So the Coulomb constant, we say that it has the value of 9 times 10 to the 9. Okay, but if we consider just only this constant, or the permittivity of the free space, we have the values here, and then 1/4 pi epsilon 0 will make the Coulomb constant. So we times this constant of proportionalities to Q1, Q2, and R square. So we have the equation like this, or we also can write this down as K Q1, Q2 over R square. So this is the Coulomb's law. Okay, so I'm going to talk a little bit about the example before we come to do this stuff in detail in our live class. So for a hydrogen atom, it has one proton. So a proton has a positive charge, and an electron has a negative charge. So you can guess that if you have a positive and negative charge, they will try to attract each other. Okay, but what actually happening here is we are going to assume that the electron is doing a circular motion around the proton. Okay, so with this circular motion, what you need is the force that is pulling electron towards the proton so that they can do circular motion. So this question, they ask you to calculate the force between nucleus and electrons. When the electron is at the distance of this, okay, this very, very small distance, 10 to the minus 11 meter. And then they want you to find the speed of the orbiting electrons, okay? Okay, so we start with force. So we use Coulomb's law. We use that equation. And then we try to substitute the value. So for the Coulomb constant, 1/4 pi epsilon 0, we substitute epsilon 0 to here. And then for Q1 and Q2 will be the charges of protons and electrons, which has the same value, which is 1.6 times 10 to the minus 19. And then we substitute the distance r, which is 5.29 times 10 to the minus 11. And don't forget the square. And then we can calculate the force from here. And then we bring the force Fe, or electric force between proton and electrons, to be the centripetal force. So from centripetal force, we have that the acceleration AC to the center, or mv squared over r, we make it equal to Fe that we calculated from A. And then we can work out the problems to find out the V, okay? But before that, you need to know, or you need to Google for the mass of an electron, which is 9.1 times 10 to the minus 31. Okay, this is the mass of electron. So you need to put in the mass of electron before you can find that the speed of the electron around the nucleus of the hydrogen atom is about this, about 2.2 million meter per second. It's very fast. Okay, so and then this is the case of you have more than 2 charges in the system. Okay, we have 3 electric charges fixed at the corner of the right triangle. So to determine the size of electric force on the negative charge. Okay, so we want to find the force on here. So that's we consider 2 forces. Okay, so the force F1 will be from the charge in the up position, and then the force F2 will be from the charge on the right hand side. So and then we need to find the F1 first, and we need to find the F2. So F1, again, we use Coulomb's law. So 1/4 pi, and then we substitute epsilon 0, and we substitute Q1, this is a Q1, and we substitute the Q2. Okay, so which is, you can see that for F1, is this a charge from this one up, which is 0.8, and then the charge from, and then the charge from the negative charge, which is 0.6 times 10 to the minus 6, and then we divide it by the separation distance. Okay, so you need to be careful about the unit. Okay, so here we say microcoulomb. Okay, so micro is the 10 to the minus 6. Okay, so we put the 10 to the minus 6 every time, and centimeter, 8 centimeter, it is 8 and times by 0.01. So you have 0.08 for this, and then you can calculate the F1. Okay, and what we need to mention also is the direction. Okay, so the direction of F1 is up, because the electron is attracted by, sorry, the negative charge is attracted by the positive charge. So we start with calculating the magnitude of the force first, but by not considering the negative sign just yet. Okay, so then we have the magnitude. Then after we have the magnitude, we consider the direction, which is the up direction, and again, if we try to see the direction of F2, we consider the negative charge and positive charge. So again, negative charge will be attracted by the positive charge, so that the direction of the force will go to the right hand side. Okay, so after we have the vector F1 and vector F2, and we combine the 2 vectors by using Pythagoras theorem. Okay, and so that's I have 1.64 Newton. Okay, so we're gonna show this calculation in the step by step in the example class, and then we can try to relate the Coulomb's law with mechanical equilibrium in this case. So we have 2 pendulums. Okay, and for the pendulums, this mass, okay, in green, and another mass in green, they have some charge in it. So when they have some charge, this mass on the left and this mass on the right, okay, will be repulsing each other by Coulomb force. Okay, so that's we say that the Coulomb force that is acting on the charge in the left hand side is Fe. Okay, and then when we consider the mechanical equilibrium, okay, we have tan theta equals Fe over mg, and for Fe we use Coulomb's law to substitute the Coulomb's law. Okay, and then we work out this calculation until we have the Q. Okay, so details later. So and then now we have a look at another concept. Okay, so we have finished with the electric force, and now we're talking about electric field. So firstly, we're gonna say that electric field is generated by electric charge and is a vector field. So that's the magnitude and the direction will depend on the position. Okay, so that's that means if I am at this very position at my pointer, and I move to another position, okay, both magnitudes and direction of electric field might change, okay, because they are the vector field. It is a vector field. Okay. And so what is interesting about what is the main concept about the direction of electric field is the electric field is out from positive charge, but going into the negative charge. Okay, so as we can see that this system has just only one positive charge alone. So that we can see that all the electric field lines, okay, the direction will be pointing out from positive charge. But when we have the negative charge alone, all the electric field lines will be pointing towards the charge, negative charge. But if I have the positive charge and negative charge sitting together, the field will come from positive, will out from positive, but being into negative. And if I have the positive and positive, the electric field will try the electric field lines will try their very best to be out from positive charge. Okay, and another point to be observed is the electric field lines will not cross. Okay, will not cross each other. Okay, so they're not going to be in this way and in this way, but they try to avoid crossing. Okay. Okay, so this is another like 3D animations that tells you about the electric field direction. Okay, in the case of positive and negative charge, that the field lines come from positive going into negative, and field lines with positive and positive charge will avoid each other and will not try to cross. Okay, then we talk about the intensity or the magnitude. So we say that the region with high intensity or the large magnitude of the electric field can be seen through the larger number of electric field lines. Okay, so if I consider the position that is like far away from both charges in this animation, we can see that there are less number of electric field lines. So less number of electric field lines means the less magnitude or less intensity. But if we look at the position between positive charge and negative charge, okay, they are going to be strong or high intensity electric field between positive and negative charge. And if we bring positive and negative charge closer, so you can see that the intensity or the number of electric field lines become high. Okay. Then for some equation for your further calculations, we have that the electric field from the point charge Q. Okay, so we consider just only Q here, which is here is a positive Q, and here is the negative Q. The electric field can be calculated from the Coulomb constant. The Coulomb constant 1/4 pi epsilon 0, and times by Q over R squared. So that we can say that at the further distance from Q, or at the further distance R, the electric field will be weaker. Okay, so that you can see from less intensity. But if you come closer to the charge, you can see higher intensity of electric field, so that the value of E will become higher. Okay, so this is actually like the magnitude, but for the direction, as we discussed before, the direction of electric field will come will come out from positive but into negative. Okay, and about the relationship with force. Okay, so we say that we cannot actually see the electric field. This is true. You cannot see the shape. You cannot actually see the shape or the color or the size or anything of the electric field by eyes. Okay, but so you cannot see it, but you can feel that it exists by bringing the test charge Q. Okay, so if I bring the test charge Q into the region where electric field exists, like this, so just place it on the electric field, and you can see that there will be force acting on the charge Q, and the force will be the product between the electric field intensity and the charge Q. Okay, and then another one thing to be considered is the type of electric charge. Okay, so for example, if I have the electric field from the plate, from the charge plate, so I start with having positively charged plate over here and negatively charged plate over here, and electric field come out from positive to negative, as we see. So we have the electric field in the right hand side direction. Okay, electric field goes to the right hand side. Okay, so with positive testing charge like this, okay, so we're going to say that direction of E or field and F is force. So E and F will have the same direction with positive charge. But with negative charge, minus Q, E and F will be with opposite direction. So this is another thing to know. Okay, and then another relationship with force. Okay, so if I consider the electric field from the point charge Q, so you can see that the point charge Q will be coming out, okay, from the charge. Okay, and then if I bring a test charge like small q at this position, so the positive charge Q will have the force in the same direction as the electric field, as we discussed before. So it will have like the same direction. Okay, so with this same direction, with this similar direction, and we can calculate the magnitude F equals QE, and this equation will be the same as Coulomb's law. Okay, so this is to confirm that it is right to talk about electric field in this term. Okay, if F equals QE, and then also if you look at the direction of the force acting on Q, okay, so then we can say that the Q is being repulsed from big Q. Okay, neutral point. Okay, so this is an example about neutral point, which we are going to do the calculations in detail later. So the neutral point is actually the point where the electric field is zero. Okay, so for example, if I have a charge Q1, okay, and a Q2 with the size of 5 and 2 nanocoulomb, okay, and if I consider a point P over here, okay, at any point P, okay, you can see that electric field from the charge number 1 or Q1 will go to the right hand side. It will go to the right hand side because the direction of electric field from positive charge will come out. Okay, so I should do this direction. So from Q1, okay, if Q1 is positive charge, electric field should go in this direction. But then if I got Q2 on the right hand side, the direction of electric field from Q2 should go from positive, out from positive. So it should go to this direction. So the charge on the left will provide electric field to the right, and the charge from the right will provide electric field to the left. Okay, so that we have the two vectors E1 and E2. Okay, in the opposite direction. Okay, so now what we do is we want to find the r, or the distance that making P the neutral point, or that makes the electric field at this point to be 0. Okay, so that's we start with finding E1, or electric field from Q1, and then we find electric field from Q2. Okay, so we have 15 to minus r, this distance. So 15 minus r will be this distance, or 15 minus r. Okay, and then we bring E1 equals to E2, because if we consider the direction of 1 and 2, they are in the opposite direction, and if the vector with opposite direction having same magnitude, they will cancel and you have 0. So that's I substitute E1 equal to 0 and then work out for R. So that we have the distance R that is making this point to have 0 electric field as 9.2 centimeter. Okay, and then there are also another example about accelerating the electron in an electric field. Okay, so we can relate this relationship between E and F, or F equals QE, okay, with the acceleration. So with the acceleration, so from Newton's law, F equals ma, we have A equals F over n, and we can substitute F as QE. So that we have the A, or acceleration, and with constant acceleration, we are allowed to use the formula for motion, such as S equals ut plus half at squared, in order to find the total distance over time. Okay, and then the last topic. Okay, so what are we going to do if we have the object with size? Okay, so when we have the object with size, what we do is we are going to consider the small element dx. Okay, so if I say that the lambda equals q over l, be the charge per unit length, we can say that for q, or the charge will be lambda times l. Okay, so in the same fashion, if we have the small length dx instead of l, we can say the small charge dq can be written in terms of lambda dx. Okay, and after that, we consider the electric field from the small charge. So we change E to dE, and we change Q to dQ. Then we substitute the dQ equals lambda dx, okay, into the same equation, into the Coulomb's law. And then when we want to find the total electric field from all the elements, okay, so because the dE over here is the electric field from only the small blue part here. But if we want to find the total electric field from all parts, okay, from all parts, what you need to do is to integrate the dE, okay, and then we will perform the integration, and after that we are going to get the relationship, okay, between electric field and the total charge of the object, and the length of the object L, and the distance A from the point P. Okay, so that's the end of it. So hopefully you enjoy it, and if you don't understand anything, okay, you can post the questions into the Facebook, and we are going to see you in the example class, so in which we are going to repeat all the calculations again, step by step. Thank you.